So first of all, just for our audience here, maybe give a little rundown about dark matter and why it's so mysterious and maybe why it's important.
Okay, so I guess I'll start actually with why it's so important. Our current estimates indicate that about 70% of the universe is dark energy, and 25% is dark matter, and about 5% is standard model stuff. And so that means that there's about a quarter of the universe, or about 5 times more than ordinary matter, of this dark matter stuff. And essentially, we have various different lines of evidence that indicate that the dark matter does exist. It originally came from astrophysics observations of basically how large astronomical bodies were gravitationally interacting with each other. And you can make some fairly simple predictions based on even just the Newtonian relationship between mass and how things move under the influence of gravitational force to figure out that in things like galaxies and in clusters of galaxies, there must be a lot more matter there than what we can see. In other words, much more than the luminous matter. Otherwise, things would not gravitationally clump together as much as we see them doing. And so clusters of galaxies would fly apart, and spiral galaxies would exhibit what we call different rotation curves. So in other words, if you look at the radial velocity of stars that are near the outer parts of those spiral galaxies, they, based on their speed of rotation, there must be more matter within the galaxy holding them there than what we can see. And then there's been also observations of cosmic microwave background radiation and some simulations that we've done for cosmology for large-scale structure of the entire universe. So by this we mean on the largest scales we can imagine basically how even clusters of galaxies seem to arrange themselves in these huge filaments. And then from the particle physics point of view, we have been suspecting for quite a while now that our standard model, as successful as it has been in many ways, is incomplete. There's some basic issues with the mathematical foundations of it. For example, why does the Higgs boson have the mass that it does? And why is the Higgs boson stable? Why is this basically hierarchy of particle masses the way that it is? So we have some particles like the Higgs, which are quite heavy, and then we have the various flavors of quarks, where the top quark is much, much heavier than, for example, the up and the down quarks. And then we have the electron and the muon and the tau, which are quite a bit lighter than, for example, the proton. And then we have the neutrinos, which have these ridiculously tiny masses. So we've got these particle masses all over the place, and we have the Higgs that is giving all these things mass, but the Higgs itself has a mass that is about 125 times that of the proton, and it just seems very strange. It doesn't all really hang together in a way that should be stable. Basically, it looks to us like the Higgs mass should not be stable at the value that it is. And we have no idea why the rest of the particles have this weird spread of masses that they do. And similarly, we don't know why the gravitational force seems to be so much weaker than the electromagnetic force, for example. We we think that we know how the electromagnetic and the weak force combine at very high energies. So they combine into the electroweak force, and we think maybe we can even combine that with the strong force and do some sort of a grand unified force, and then we have no idea what's going on with gravity. We don't really know what's going on with the fact that we have a matter-dominated universe, rather than having had all the matter and antimatter just annihilate into pure photons, basically. So we have some sort of a matter-antimatter asymmetry happening that we don't entirely understand. This is also known as charge parity violation. So there's all these mysteries behind the standard model. And so a few decades ago, it was realized that some of these standard model mysteries could be solved by adding extra particles, and that those particles could also be what makes up the dark matter, because they would have very feeble interactions with the existing standard model particles. And so this kind of gave birth to dark matter searches as a combination of astrophysics and cosmology motivation and constraints from what we actually see in terms of how much dark matter there should be in order to make the universe hang together the way it does, but not make it collapse back in on itself. And then the particle physics side of what might we need in order to complete the standard model and have things make more sense. And actually, for a while, people thought that neutrinos might be dark matter. And neutrinos were, in a way, a form of dark matter in that they had quite feeble interactions with the other standard model particles. And they did have some non-zero mass, and they did make up some very, very tiny percentage of the mass energy budget of the universe that could not be accounted for by things that we could see, essentially. So you could think of them as sort of the first component of dark matter that we ever found. It just happens that they only make up something like 1% or less of the mass energy budget of the universe. So there's still all this other dark matter out there. But the same detection techniques that we used for neutrinos could be adapted and refined to look for dark matter particles that sort of behaved in a similar way, except that their interactions were even more feeble, for example, or they had higher mass, or they were even trickier to find for other reasons. So that's how I sort of started my career in neutrino physics and then ended up in dark matter physics. It was sort of my idea of leveling up. You take, one type of particle that was really hard to detect, and okay, now we found it, and now we can actually study in detail some of its properties. Okay, but now we got to get to the next level of sensitivity where we can find particles that are even